The last person who we'll visit is Dr. Stephen Hogan, who is attempting to build qubits with Rydberg atoms.
First question is, what kind of qubits are we using in my research group? We use atoms in highly excited states as our qubits. So we're very careful to pick states, and then we choose transitions between these states that occur at microwave frequencies. So in general in our research we're interested in coupling microwave photons to these atomic qubits, so these Rydberg atoms. What are the advantages and disadvantages of these qubits? For us, the advantages are that these qubits operate at microwave frequencies. So in our quantum information processing, the microwave photons carry the information and then they're absorbed by the atoms to convert the atoms from one qubit state to another qubit state. And so the advantage particularly of these atoms is they have very strong transitions at microwave frequencies. So it's very efficient to couple the photons and the atoms, and then because of this it's possible to do fast gate operations. And the disadvantages are that these states are not the ground state of an atom or a molecule, they're a highly excited state. So they can eventually decay back to the ground state. So they don't have infinite lifetimes. But their lifetimes or their coherence times are quite long. So they live for tens of milliseconds or hundreds of milliseconds. So we can in principle do quite a high number of operations within these lifetimes. What we try to then do is we try to couple two systems together. We try to couple microwave circuits that are chip-based and very scalable with these atoms that are in the gas phase or levitated in the vacuum chamber. And one of the problems is to try to make chip-based devices which combine the atoms with these microwave circuits. And this is one of the main objectives in my group. So we try to develop chip-based decelerators and traps that we can combine with these microwave circuits. So we can trap atoms above these circuits for these quantum information applications. The next question is, how are we making these qubits? So to make these qubits, we have to be very careful to prepare the atoms in these very highly excited states. So in our experiments, we have beams of atoms and we excite them with very narrow bandwidth lasers to these states with high principal quantum numbers. But this isn't enough. We still need to make them that they have maximum angular momentum for the value of the principal quantum number. So to do this, we have to have a combination of electric and magnetic fields in which we do the excitation, and then we slowly turn off the electric field and then leave the atoms in what we call these circular Rydberg states. So they have a maximum value of principal quantum number and also a maximum value of the electron orbital angular momentum quantum number. And these are then our qubit states. When do I think we'll have the first universal quantum computer? So the first universal quantum computer I think will take some time before it's produced, probably many tens of years. But in the meantime, there are many other kinds of interesting quantum computations that one can do, particularly maybe in the area of quantum simulations, where you kind of generate interactions between atoms or qubits and try to generate these interactions in a way that they represent some other interesting physical system. So in these quantum simulation devices, you would get the result of something you would do with a quantum computer, but without sort of programming a quantum computer. But to actually have a quantum computer that would be sitting on your desk is probably, as I say, tens of years away. So the final question is, what would I do if I had a quantum computer on my desk right now? As an experimentalist, if I had a quantum computer on my desk right now, I would have to go to the lab and start doing new experiments in some different area possibly, or to try to improve this quantum computer. So this is, I suppose, in some way asking what would I do with a classical computer. So right in the lab, I would use the classical computer to run the experiments for me. So I don't know if this is a reasonable thing to do with a quantum computer, but our objectives are always to try to push the experiment forward and try to do new experiments that haven't been done before. So this is the real goal of all of this research in many ways.